Okay, class, welcome to lecture 23. So today we are talking about functions and operations on sets. Not very fancy. Because it's so cool, I shaved today so that I could look young and hip for all this cool math we're gonna learn. So anyway, next, let me explain what this is all about. You study, the idea is we learned a bunch of stuff. Now we want to see how they interact with each other. So we want to study how functions interact with operations that we've learned, like union and intersection. And in fact, although subset is not really an operation in the same way those other guys are, we also want to see how functions interact with subsets. That's just too much for one big title, so I didn't put it in there. But that's the idea for today. Okay, so we're going to try to build up to it with an example instead of jumping right into the definitions and things. So let's think about some sets to work with. So here's this one, and here's another one. I'm going to use the letter T actually because that's what I use later. A, B, C, D. So they both have 4 elements in them. And then we'll define a function using pictures just because it's quicker and looks nicer. It really tells you what's going on. So here's a function from S to T. So I got to say where everything goes and make sure I don't send anything to 2 different places. So I'm going to send 1 to B, 2 to B. So I don't know why that happened. So, okay. As I was saying, I'm going to send 1 to B. 1. I said 1 to B. There we go. Okay, back on track. 2 is also going to go to B. 3 will send right across to C, and 4 will also send right across to D. So let's think about subsets of S. And think about how they interact with the function, meaning if I have a subset, so what's a subset? Just a couple of the elements. So there's a subset. Then the idea is, normally I think of the function as sending an element to an element and another element to another element. But what if I sort of think of it as sending a whole subset over? Then what do I get as a result? Well, then I should get another subset. So let's do a couple of these. So that'll be A. What about like this one? 1, 2, and 3. It's another subset. I don't know, 3 and 4. Another subset of S. So then, if I want to think about the set that they go to instead of the element that they go to when I'm sending elements over, I really should be thinking of a set of elements that come from plugging in elements of the first subset. So like what kinds of things should be in this first set where I think of sending A, 1 and 2 all together in one big chunk? Well, because they both go to B, the only thing in this set should probably just be B. Now I haven't named it yet, so that's why this is blank right now. But what if I send 1, 2, and 3 over? What set should that become over in T? Well, now I'm sending things to B and I'm sending things to C. So the set over here should really consist of B and C. And then 3 and 4, if I think of that as like one big chunk, that just goes to C and D. So the set that C, big capital C, goes to should just consist of C, and D. So this is like the idea that we're going to be exploring. We're sending subsets instead of just elements. But of course, where the subset goes, which subset you get as a result, depends on the elements in the subset. So where does A go? It goes to the set consisting of just B, because the things in A all went to B, that element. So where does capital B go when I send it over? I don't know why I circled the whole thing. Underline as I was doing before. Where does B go when I send it over with the function? It goes to this set, because the stuff that's in B in green goes to the two elements in that set. That's the idea. So now I'll reveal the name. The name sort of makes sense. This should just be called f of capital A, because it sort of is what I'm doing. I'm plugging in a set to the function. This should just be capital F of capital B, and this should be F of capital C. Now we'll define these properly later, but that's the idea. Okay, so then the other thing we can do is think about where sets come from. So we can also look at, instead of looking at subsets of the domain, we can look at subsets of the codomain and sort of do the same game, but backwards. So maybe I'll call this x1. So it's a subset of T now. So it's just some of the guys in T. So remember, T consisted of A, B, C, and D. X2 will be this something else, I don't know, A, B, and C. So going back up to the picture here, the idea is I have some sets. One of them, I guess I called X1 is just consisting of B and D. So I need another color. I don't know, B and D. So if I think of that as a grouping, as a set, the set consisting of B and D, I can think about sort of the opposite of what I did last time, which is think about the things that go into that set. And so what is that? Well, 1 goes into that set, so does 2, and so does 4. So that's the idea behind what we're doing now, thinking of this thing backwards, which is I want to think of the elements of the domain. So these are all going to be in S that go to the elements of the subset X1 that I'm talking about. So here, now I'm thinking, what elements go to A, B, and C? Well, let's see. In fact, nothing goes to A. So that doesn't tell me anything, but B and C get hit by these 3 elements. So 1, 2, and 3. So now this would consist of 1, 2, and 3. Now the name of this set that you get is a bit confusing, but because it's sort of a backwards process, we use this notation. Oops, I didn't leave myself in a room. So we use this F inverse notation, even though the function might not even be invertible and the inverse of the function doesn't actually exist. We just call the set we get doing this method F inverse of the set, because the idea is you're sending the set in the codomain backwards and figuring out where it came from. So this one would be called this. Okay, so I will define these things properly now, but I wanted to do this example, and then we'll come back to it and describe it using the real definitions. Okay, so here's the definition that we are secretly working on this whole time. So if you have a function that goes from a set to another set, so I'll call it S and T, and you have a subset of the domain, so A lives in S, so it's just some of the stuff in S, then the set you create by sending A over is called the image. And I know we've used the word image before, but this is called the image of A under F. but if you already know the function is called f, you just talk about, just maybe shorten it to the image of a if you don't want to, if you don't care what the function is called. So this is the set that we just described, the set you get by sending the elements of A across. So let's see if we can describe it in complete generality. And just by thinking about what it's doing. So first of all, where do the elements of this set live? Maybe I'll write down the idea first before I try to use the fancy notation. Well, it's all the elements that the elements of A go to. And they all go into T because T is the codomain. So really it's the set of elements of T, maybe not all of them, just some of them, which are outputs, aka f of something. So outputs of f, but not all the outputs of f, just the ones that are coming from elements of A. Because that's exactly what it means to think about the set that you get by plugging in only things from the subset A. So how can I build this up? Well, there's a couple ways to say it, but this is the most terse way, I guess. So it's the outputs that you get, and they live in T. So you don't have to say this part, the in T part, because it's implied that it's in T, but if you just want to be extra careful, so it's the outputs that are in T, but not all of them, just the ones where you plugged in things from A. Okay, so that is called the image of F, image of A under F. Not to be confused with the image of F, which is something we learned about before. Different than the image of F, which is the set of all outputs that you can get. This is just the set of outputs when you only limit yourself to certain inputs in the subset A. So let's sort of just think about this definition in the context of the examples we just did here. So why was f of A equal to just little b here? Well, by definition, this is really, whoops, accident A. What the set actually is. And so the things that are in here are just B, because B is f of something in A, f of 1. And then f of 2, since it's also B, it just tells you that B is in there again, but you don't have to repeat. So it just consists of B only. So this guy, by definition, again, it's just the set of f of x's, the set of outputs where the inputs come from the set that you're plugging in. So why is the set consisting of elements B and C? It's because you have to look at B. B has 1, 2, and 3 in it. So little b equals f of 1, and 1 is something from B, from big B. And C is f of 3, and 3 is also in that set. So it's just the stuff that comes from plugging in things from the subset. Okay. And then there's the opposite thing, the other one that we did. It's a little bit more complicated to understand. I would recommend creating more examples of functions and trying to figure these things out. So you create two sets, create functions between them, try to figure out images of different subsets. just as little mini examples for extra practice. Okay, because we got to move on to the abstract stuff instead. So this will be another function, and I'm going to call the set C to match things later. Now I'm looking at a subset of the codomain. Then, if I sort of send it back to the domain, the name of that set is called the preimage. So the preimage of C under F. So it's just the opposite idea, except we use this really annoying notation because it has nothing to do with the inverse function, because it might not even have an inverse, but we just call it this, as it, because I guess it just sort of means go backwards. But it's called the preimage of C. So how should we define it? Well, the idea is it's supposed to be all the stuff that goes to C in the domain. So let's write that in words before I try to say it fancily with notation. So it's really the set of elements in S, because I'm starting with stuff in T and I'm sort of sending them back. I'm seeing what elements got sent to C in the first place. So now I'm living in S. So it's the set of elements in S, but not all of them. What do they do? Which you could think of as getting sent to C by F. So how can I write that in this notation? Well, that just means that if I plug X in, it should be living in C. And that's exactly what this is saying, but this is in words instead. So it's the stuff in S that gets sent to that subset. And this one's a bit trickier because things can get sent to the same subset in different ways, which will come up sometimes. Okay, but let's throw in some more stuff now. So now we're going to mix in a little something extra, some spice. And by spice, I mean operations. So union and intersection. So we want to think about combining these guys with what we just did. So let me display that with a picture. So we sort of want to compare this idea. So say I have my set S, which I'll just draw this as a blob. And I have my set T, I'll just draw as this other blob. So right now we just learned about if I have a function and I have a subset inside of the bigger set, well, I can send it over and I can figure out what f of a is. It's just some other set over here now. It's the stuff that all the stuff in A goes to. But then, of course, I can have another set, another subset, and I can send that guy over too. So then it really forces you to think about stuff like, well, what happens if I look at their intersection? So that would be this little stuff right here. If I send, that is itself another subset. So if I send that over, how is it related to if I send them over independently? Meaning I do f of a, then I do f of b, then I intersect that. So that's this green stuff. And so are they the same? Is that the same thing? That's a good question to ask. And then you can ask the same thing about unions. And you can ask the same thing about going backwards with the pre-image instead of the image. So that's the stuff we want to answer. So how does that compare? How does it compare if I union, then I send that set over, versus if I union each of them independent, or send them over independently, then I union them? How do these things compare? And there's interesting answers to these questions. it's not so straightforward. So here's the first result theorem. So I have a function from S to T. And I have two subsets inside of S. So I'm sort of creating this picture here. One thing I would recommend is if you really want to get the most out of this, you should try to come up with how you think these two are related, how these guys are related before you continue watching this video. So the way you could sort of think about it is just make some examples and compare your results and see what's going on. Okay, but here's the spoiler. Here is exactly what's going on. That's what a theorem is. Then, if I intersect them before I send them over, that's actually a subset of if I send them both over and then I intersect them. But if I union them, they're exactly the same. Sort of weird that, because there's usually lots of symmetry in math. So you usually predict things to work the same, but in this case, they don't. Okay, so let's prove this result. So the first one is the weirder one. Okay, so it looks very complicated, but it's just a subset proof. So I have to do a subset proof. So to show that this guy is a subset of this guy, well, because it's a subset proof, I have to let something be, I'm going to call it Y, because it's in the codomain and people like to use Y for the codomain. You don't have to do that, but I'm going to do that. Let Y be in this subset. Now remember, these guys are comparable because they are both subsets of T. If they were not both subsets of the same thing, I wouldn't be able to compare them. If one of them was an S and the other was in T, they wouldn't be comparable. So very first and foremost, you have to realize that they both live in the same place. They both live in T. Okay, so let Y be in the first one, show Y is in the second one. Now, to do a subset proof, you really have to understand the set that you are working with, or the subset that you're working with, so you can expand upon what it means for an element to be in there. So what does it really mean? This is what I got to assume. What does this really mean? Well, the best way to figure that out is just to rewrite the definition of this subset in the context. So I know the definition of F of something is it's the stuff in T. So it's the stuff I get in T by plugging in X for my domain, but not everything in my domain, just the things that are in the set that I'm sending over. What's the set I'm functioning over? It's the whatever's inside the F of thing, so that's A intersect B. So that's what this set that I'm dealing with really is. So what does it mean for Y to be in here? Well, that means Y is one of these things. Y is a result of plugging in an element of the domain coming from this subset. That's what the image is. And so now maybe I don't know where to go in the proof, but I do know that I have more information to work with. Because now I know that Y came from an X, which was in an intersection. So I can say more about X. It's in an intersection, that means it's in both of the sets. Now, I'm really trying to get over here, which is another intersection. So I got to show that Y is in both of these. Well, this really requires that we really understand F of A. So maybe you could do some scratch work over here. What is F of A? That's just by definition the set of F of X's where X comes from A. It's the stuff you get by plugging in things from A. So I have something in A right now. I have an X that's in A. So that means that if I plug it in, it's in the image of A. But f of x is actually just y this whole time. So actually, I've shown that y is an f of A. Same idea for x being in B. This means f of x is also in the image of B because x is in B. And so that's just y. So now y is in both of these things. So that means it's in their intersection. Great, that's what I wanted to show, right? Wonderful. Okay, so I've shown part one. So now it's interesting that they're not equal, but instead there's just one is a subset of the other. The next proof, the claim is that they are equal. So I have to do subset inclusion both directions. So first we'll do one way, meaning I'll let x, sorry, I'm gonna call it y again because because f of something is in the codomain. So I'll call it y again because people like to use y for the codomain. So let y be in there, show as a result that it's in the other one, and that will show that they are, that the first one is a subset of the other, and then we're going to do it backwards to show that they're subsets of each other, which shows that they are equal. Okay, it's going to work the same. So because y is in there, I have to say more about it, but what can I really say? Well, it's an image, so it looks like f of something, and that something comes from the set that you're plugging into the function that you're sending over, that you're creating the image of. So that's really what that set is. So if y is in there, it equals one of those things. And the input to create y, the element of the domain to give you y in the codomain, comes from that subset. So it comes from A union B. This creates a proof by cases. Because x is in A or B, you can have two situations. If x is in A, then something will happen, and if x is in B, something else will happen. Well, I'm trying to get to here, and so what I'm going to do in this case is notice that since x is in A, just by definition, that means it gets sent to the image of A. But then if something is in one set, then it's automatically in one set or whatever other set you feel like adding onto it, because it just has to be in one or the other to be in that union. So that's true. But that's just y. Y is f of x, so y is already in here. So we've shown the proof in the first case. The other situation is, what if x is actually in B instead of in A? Well, it works just the same. Then by definition, f of x is in the image of B, because the image of B is just the stuff that the things in B go to, and x is one of those things. But then that means it's in the union of that and whatever else you want, because it's in one of them. But that just means y is in the thing that we wanted y to be in. So we're done. So that shows this. Now I got to do it backwards. But it's going to work just the same. It's going to be proof by cases. So the first case is because it's in a union, if it's in the first one, something will happen. Oops, A. So what will happen? Well, what does it mean to be in an image? It just means it equals f of something where that something is in A. That's just the definition of the image. You have to get used to it. And what does that mean then? So really, X is in A is what we're going to use next. Because then we can pull this little trick again. If X is in A, it's automatically an A union B. And then if it's in the union of A and B, then if I send it over with f, the function, then f of x is in the image of A union B, just by definition. The image is just the stuff that you get by sending things over from the subset, and this is one of those things, so it's in there. Okay, and that's what we wanted to show. So I let y be in the other subset, and I showed it's in the first one. I guess I didn't finish writing that thus. So that's case one. Case two is if y is in here instead, but it works just the same. You can literally sort of copy paste what I just did and replace A with B. And it works exactly the same. So I'll just write it down very quickly. So the point is that in either case, we've shown what we wanted to show. So we've shown that they're both subsets of each other, so therefore they're equal sets. Okay, so unioning and then functioning over is the same as functioning independently and then unioning after that. Okay, so they're equal sets. All right, so now for pre-images, I'm gonna run out of steam. So I'm only gonna do one of the proofs and leave the other one to you in the lecture problems. But it's gonna work very similarly. Okay, so here's another fancy theorem. Let f be a function. This time we're gonna start with subsets of the codomain. And we're gonna look at their pre-images, combining with unions and intersections. So this time, everything works out very nicely. Everything is equality of sets instead of just subsets. So if I intersect, I do get set equality. So I can think of intersection of the two sets and then look at the preimage of that, or I could look at the preimage of each one separately and then think of the intersection of that, and either way will be the same. And then same thing for unions. Okay, so which one do I want to prove? I'm going to prove the first one. The second one will be given to you as a lecture problem, but it works pretty much the same. Okay, so we're doing a subset proof both ways to show set equality. Now my two subsets live in S because they are pre-images. So they started off with things in T and then we looked at where they came from. So now we're back in S. So because we are in S, I'm gonna call my elements X and I'm gonna let X be something in this pre-image. Then I'm gonna show that X is in the other one as a result. Okay, so it's just going to be playing around with the definition of pre-image, sort of how we did the other ones. So because I know X is in here, what can I do? Well, I really need to understand this set better to say that. So I'm going to rewrite the definition of pre-image for this context. So the pre-image of a set is the stuff in the domain such that if I plug it in, I go to that subset in the codomain. So after I plug it in, I'm always in the subset I'm talking about, which is this C intersect D this time. So X is one of these things. Here I'm using X as just a variable, whereas here I'm using X as a specific element. But in any case, X that I'm looking at is one of these. So I know that f of X lives in C intersect D because X is in the preimage of C intersect D. So what can I do next? Well, now I know f of X is in an image, is in an intersection. So you sort of just trust that things are going to work out by saying what that tells you and hoping that information helps you later. And it will. So because it's in an intersection, that means it's in both of them. And how does that help us? Well, I'm trying to get over here, and I'm actually almost there. So since f of X is in C, this is just the definition of preimage. If X gets sent to the subset C, that's what this is saying, that just automatically means that X is in the preimage of C. Because the preimage is the stuff that gets sent to C. X is one of these things that gets sent to C. So it's in the preimage of C. And then same idea with D. So since f of X is in D, this means the same thing. X is in the inverse, sorry, not the inverse, the preimage of D. So now it's in both. And that's what I wanted to show, correct? Yes. Okay, so that shows one is a subset of the other. Now we go backwards, we let X be in the other one. Show it's in the first one this time. But it's going to work sort of how the proof work, go backwards. So since X is in this intersection, the first thing we could say is that it's in both subsets. And then we can just peel apart each one independently to continue. Okay, so since it's in the preimage of C, this just means, so the preimage of C is the stuff that gets sent to C. So that means if I plug it into F, it's going to get sent to C. And similarly, X is in the preimage of D, so if I plug it in, it's going to be in D. So f of X is in both of these guys. So X gets sent to the intersection, that just means it's in the preimage of the intersection. That's, and again, the definition of preimage. This means that X is in the preimage C intersect D automatically. That's just the definition. Okay, so we've shown what we wanted to show. I'll leave it to you to finish the proof, but you just basically have to write that there. Then now the sets that we were looking at are equal. Okay, so I'm not going to do the proof of 2. I'll leave that to you in the lecture problems. I'm going to skip to another theorem just to give you some more guide proofs for things. Okay, so here is a very related thing. Here's a function. Now we're going to look at what happens if you do this very weird thing. You look at an image and then you look at a preimage back and forth. So what we need to look at is a couple of sets, subsets. And then what we want to do is we want to compare these two things. So where does A live? A lives in S, but something else lives in S that's super weird. What happens if I look at the image of A So where does that live? That lives in T because I've sent A over. So those are not comparable right now. They're in two different places. But what if after I do that, I look at, that's a set, right? That's a subset in T. So I'm allowed to look at its pre-image. And that is back in S. So it would be super nice if they had just like canceled and they were equal, but that's unfortunately not true. And so I would recommend making an example of a function in subsets and seeing that they're not the same, seeing that they're not equal. And then the same thing happens if you do the other direction. So if I look at C, that guy lives in T. And I'm allowed to look at its pre-image, but they are not comparable because that the pre-image lives in S. But then that's a subset in S, so I can look at its image. Now those are both living in T, so I could compare them, and it turns out that this happens. Again, they're not the same. They don't just like cancel when you do images and pre-images. Unfortunately, but that's how it goes. We don't have a choice. That's just how math works out. Okay, so we're gonna do the proof of the second one. The proof of one will be a lecture problem. Okay, so it's a subset proof. So I gotta let something be in the first guy. I'm gonna call it Y because it's in the codomain, because it's an image. So it's something in T. So I'm gonna let Y be an element of the thing I'm trying to check as a subset of the other. And then I'm gonna show that it's automatically an element of C as a result. Okay, so all we have to work with is this. And we just have to peel back the layers by thinking about what the heck this thing is. So it's F of something. So it's an image. So that means that the elements in the image are always elements of the set you get by plugging things in, where those things come from the set whose image you're looking at, aka the thing that's underlined in blue. So that's what this subset really is. So Y is one of these things. Y is f of x, where the x coming from the subset that you're sending over, aka this guy. That's the thing that's that the image is being taken of. So what does this mean then? This I can also peel back. Well, if it's in the pre-image of something, that means that when I plug it into that function, it gets sent to that subset. Oh, but then we're done, because what is f of x? That's just a y. Isn't that what I wanted to show? Yeah. So this ends the proof. Okay. So the more interesting thing is, why are they not equal? Why is this the only direction that works? So I would encourage you to create examples. The hint is make a function which is not surjective and also not injective to see why these two things are not equal necessarily. Okay, but that's the end of the lecture for today. So see you next time.